So the next one is 3. In this one we have these two matrices, block diagonal matrices, each one having two blocks, two diagonal blocks. And the blocks are our usual matrices M, those M matrices. And it's also of course given that N1 is greater than or equal to N2 and M1 is greater than or equal to M2. These matrices, two such matrices are similar if and only if N1 is equal to M1 and N2 is equal to M2. In other words, they are similar if and only if they are the same matrix. That's what we have to prove. Now, if and only if means we have to prove two implications, one of which is obvious. If N1 and M1 are equal and so are N2 and M2, then these two matrices are actually the same matrix. And since similarity is an equivalence relation and hence reflexive, so obviously this matrix is similar to itself. So one half we can simply mention at the end of the solution set, or if you want we can mention it now also. Let's just start the solution like that. If N1 is equal to M1 and N2 is equal to M2, then the given matrices are the same and hence also similar. Okay, so that's it. It's very easy. There is in fact nothing to do. Now, suppose that the matrices are similar. Now we can talk about similarity only when the these are square matrices of course, they have the same size. That means now that we have supposed that they are similar, they must have the same size. That, however, immediately does not mean these equalities. That simply means that N1 plus N2 is equal to M1 plus M2. Because N1 plus N2 is the size of this one and M1 plus M2 is the size of this one. Let's give that size N names. Let's call it N. Let N1 plus N2 equal to this be called N. Okay, now since they are similar, so we will have that condition for similarity. There exists an invertible matrix A, say its ith row, jth column element B, Ai, J, in the algebra of n by n matrices Fn, such that A inverse is equal to M1 M2 or A times this matrix is equal to the other matrix times A. Okay, so now we have to actually calculate these products, and from by equating those products only we are going to be able to say something. Now this looks not exactly something easy. I mean, A is a general n by n matrix and so is this one. It has a particular form but still n is general n. So in such situations it's better to first see what happens by considering some small values of n1 and n2. Small but not so small that you don't get to see anything. So let's do that first and see how the product looks. And this part is not to be considered within the solution. This is only for our understanding. So what I am going to do is this. I am considering the case where n1 is 3 and n2 is 2. So that we are now going to consider 5 by 5 matrices. It may look unnecessary, but it's actually necessary for our understanding. Okay, so this is our matrix A when n1 plus n2 is 5. This times mn1 mn2, that means in our case m3 and m2. Let's first see what m3 is. M3 is this 0 1 0 0 0 1 0 0 0. This is M3. Remember, we should have 0 everywhere except the super diagonal. That this is the leading diagonal. Above that we have super diagonal, and there we have only ones. Elsewhere it's all 0. And what is M2? M2 is 0 1 0 0. Here the diagonal is this. The super diagonal has only one element, so there we have 1. So this is our matrix mn1 mn2, or in our case m3 m2. Okay, and these are the diagonal blocks. So let me put a horizontal line and a vertical line to show the blocks, and where we do not write entries, now I am going to write, we of course have 0. That's the understanding. Zero 0 0 0 0. Now let's do the multiplication and see what we get. So this is going to be of course our usual rule, first row times first column. Now any row times first column is going to give you what? 0, because the first column is a 0 column, and because that is just the first column of the product matrix. So the first column is going to be 0. Two, 3, 4, 5. Okay. Then first row times second column, and when you do this product, almost every entry of this second column is 0 except the first one, which will get multiplied with this A11. So this will be A11. In other words, this row, when I multiplied this by this second column, I got the first entry of that row. If I do that thing with the other rows and this second column, again there also I am going to get the first entries of these rows. So 2, 1, 3, 1, 4, 1, 5, 1. Okay. So it seems like the first column of A has been shifted to the right, and its place has been taken by a 0 column. Is that what we are going to see next with the second column also? The next thing, of course, is first row times third column. When you do that, what will you get? With which entry is 1 going to be multiplied? This gets multiplied with 0, A12 gets multiplied with 1, and the rest are all 0. So A12. That means the second entry when we take the product of the first row and second column. Third column. Similarly with the other rows also. So A22, 32, 42, 52. Next again we have a 0 column. So any row you multiply with this 0 column is going to produce 0, and that's how we get another 0 column. And finally we take the product of all the rows with this column. Let's see what happens with the first row. In fact, let me use both hands. 0, 0, 0, A14. With that we multiply 1 and then 0. That means A14. Just like that with the other rows also, if we multiply this final one, we are going to get A24, A34, 44, 54. So what is the pattern of the product matrix? What do we see from this? And can we guess the general one? We have already noted that the first column gets taken by a 0 column, and then there are shifts. The first column of the original matrix, original A, gets shifted to the right and becomes the second column. The second column becomes the third column. The third column vanishes. Its place is taken by a 0 column. And then we have the fourth column. So we have 0, then this, 0, then this, and that's it, because there is no more place for this, for the fifth one. That's because there has been a shift, so here itself everything ends. Okay. What was our N1? N1 was 3 and N2 was 2. Here, what is this column? This is the fourth column, and 4 is 3 plus 1. With this pattern, we can now write the general one. Now, A times mn1 mn2 is equal to, this is how the general one is going to appear. The first column is going to be 0. 0. This matrix, to write this matrix, we are going to need horizontal space, not so much vertical space. Then we have the first column of the original A1, 1, A2, 1, An1. That's why I am writing this very close to this, because I need to write many more things also. Plus the double suffixes are also going to be somewhat big. The next one also I should show actually. So what will be the next one? The next one will be my second column actually. The second column of A now becomes the third column. 1, 2, 2, 2, N2. Okay, so like that it goes. Finally, we reach this. Here of course, here itself it ends, and then after that a 0 column comes, but it depends on the actual value of N1. So, do you see the relationship between this 2 and that one? What was N1 there in that specific example? 3. Just before hitting 3, you have to stop. That means A1, N1 minus 1. I put a bracket, but of course you understand that this is a double suffix. This doesn't mean multiplication. Just like here we are not multiplying 1 and 2, there also this is the first index and that is the second index. Suffix, index, anything you can call it. Just like that, A2 N1 minus 1. A N N1 minus 1. No matter how hard I try, I cannot really write the entire matrix here itself. So instead, let me just relax the thing a little bit. This is followed by a 0 column, and then we follow that with the next column that comes. A1 N1 plus 1. We don't get to see that second index N1 here, just like here we did not see 3. A 2 n1 plus 1 a n n1 plus 1. And now I am going to continue, but of course from here. After that, also there may be some other columns. Here it ended here itself, but that may not be true in the general case. Eventually, you reach a1 n minus 1. Oh, and how do you know where you are going to stop? Do you remember that we missed the 5s there? We said that because we have run out of space, we have to stop here itself. So you stop at n minus 1. 5 minus 1 is 4. N minus 1. A n minus 1. All right. So this is our a times this. It's not exactly something easy, can't say that, and that is why we have to do it very carefully. Similarly, if one goes through, in fact, this example itself and calculates the other product, that we are not going to go, do the special case here. Okay, we are just going to write the general form. I am leaving it to you to figure out how this next product, why this next product looks like how it looks. Also, m1, m2, a is equal to. For this one, however, we won't need horizontal space, but we need vertical space. Okay, so we remember that this is this product. We should have both the products in front of us though, simultaneously. Okay, so this is how it's going to ultimately appear. A21, A, 22, A2n, A31, A32, A3n. In other words, we have had to start with the second row of the original A, not the first row. Okay, if you see the specific calculation with that 5 by 5 matrix, you will see why it's like that. And eventually you reach a m11, a m12, like that, a m1n, followed by a 0 row. Then a m1 plus 2, 1, a m1 plus 2, here you have m1 plus 1 doesn't appear, then m1 plus 2, m1 plus 2 n, okay, and like that then it falls, and finally we have a n1, n2, n, and there is one more row. Why? Because you see, this you can call the first, well, it is the first row of this matrix, but it corresponds to the number 2. So when you have the number 2, the row is first row. When you have the number 3, it is second row. So whatever first index number you are having for an entry, the row number is 1 less than that. So here the first index is n, so this is n minus 1 row. So there is one more row, and that is again another 0 row. Okay, so this is the second product. And according to our supposition, these two products are equal, these two matrices are equal. Now, what can we infer from this equality? That's what matters. There are some zeros here and there. Can we say something from that? Okay. But so far we haven't made any supposition on the relative sizes of n1, m1, these things. Actually, we have to prove that n1 is equal to m1 and n2 is equal to m2. Suppose m1 is strictly greater than n1. That means we are expecting some kind of contradiction. It's already given that n1 is greater than or equal to n2. Okay, so with this and equality of these two products, what can we now say? This part I can use since I know that this is the second product, right? So I can get rid of this part, this one here. Let us first note one easy thing. This matrix is after all is equal to this matrix. So the first columns of both of them should be identical. Here the first column is 0. Here the first column has 2 zeros, but the other ones we don't really know. They may be 0, may not be 0. Actually, all of them have to be 0 because the columns should be identical. And from that, in particular, you get this. This is equal to 0 because after all, this is the first column, that should be this. Now, m11 is equal to 0. Okay, fine. Next, let's consider this element, am12. To which element does this correspond here? That's the question. What is the row number and column number of this element in this matrix? It's not m12, okay. Do not fall for that trap. It's not m12. Let's first see in which row this element is lying. When you have 2 here, you have to subtract 1 to get the row number because this is the first row. By that rule, this row is m1 minus 1 row. Right? You have to subtract 1. This is not row m1, this is row m1 minus 1. Column, however, is in fact 2. Okay. So this is because you can see that that's 2. That means in this matrix, this is the element that corresponds to row m1 minus 1 and column 2. What is that corresponding element here? m1 minus 1, let's just remember this, okay. m1 minus 1 row and column 2. m1 minus 1 will appear here somewhere, right? Because here we have all the rows starting from the first row, which you can see here, it's indicated by this 1, second row 2, all the way up to nth row. So m1 appears here somewhere, some row is there which is m1. Oh, actually we need m1 minus 1, so that will also be there, fine. And second column. So what is the second column here? Be careful again. These are not the indices that indicate the row and column positions. The second column now is this. So this element, that is am1 2, is equal to the m1 minus 1 row second column element of this matrix. Now the row number appears as it should appear, m1 minus 1 second column. In the second column, all the second indices are 1. So you get this new relation. A m12 is equal to A m1 minus 1 1. Let's write that. Oh, and note one more thing. How are you getting this? You are subtracting 1 from both the indices. m1 becomes m1 minus 1, 2 becomes 1. Okay, let's put comma. A m12 is equal to A m1 minus 1 1. However, when we have an entry where the second index is 1, second index is 1 means what? It means that it will appear here. Here means actually it will appear just above this thing, in this matrix. That means it's after all appearing in the first column. And by the equality of these two matrices, all these first column entries are 0. And that is why this is also 0. Similarly, if you consider the next one, A m13, by arguing like that, you successively have, first you have A m1 minus 1, 2, and then A m1 minus 2, 1. But the moment you have second index 1, this is equal to 0. And say you keep doing your calculation like this. Eventually, you reach A m1 n1. Okay, and if you continue your calculation on this side, space is really tight, but we have to manage. Then this is equal to, so you keep reducing each index by 1. First you get A m1 minus 1, n1 minus 1, and like that you keep going. Now if you want to make this n1 1 eventually, what do you have to subtract from it? n1 minus 1. That same thing you have to subtract from m1 also. So finally we get, when you subtract n1 minus 1 from m1, you get m1 minus n1 plus 1, and the second index becomes 1. That is again equal to 0. So you have shown that all these entries A m1 1, m1 2, all the way up to m1 n1 are equal to 0. But there are other entries also. What about them? Next, Next we consider a m1 n1 plus 1. What can you do about this? The first thing you have to do is you have to find out this entry in somewhere in these two matrices. So of course this will appear here itself. I mean, here you have actually everything all the way up to the second index n, that's the largest value the second index can have. So n1 plus 1 is going to appear here, but you have to figure out in which column. Of course, here these second indices show the true column position. There is nothing shifted or anything here. 1 indicates first column, 2 indicates second column, and so on. So this actually is n1 plus 1, it's sitting in that column. However, this m1, it doesn't represent row m1. You already know that it represents row m1 minus 1. So this element that we will get here is having row number in this matrix. It has row number m1 minus 1 and column number n1 plus 1. Now you have to see what the corresponding entry there is. Here, however, the second index doesn't show true column position. 1 represents second column, 2 represents third column, and so on. That means you have to add 1 to the second index value to get the column position. So by that rule, what should this column be? The second index here is n1 minus 1. Adding 1 to it, this becomes column n1. So the next one is column n1 plus 1. And there all the entries are 0. And that is why this is equal to 0 again. And then it follows the same pattern. Let me write one more. m1 n1 plus 2. This first becomes m1 minus 1 n1 plus 1, and then okay, you need not write anymore, because the moment you have n1 plus 1, because of this row, which is in fact the n1 plus 1, I mean column, sorry, n1 plus 1 column, so this is 0. And like that, eventually we have this m1 n. m1 minus 1 n minus 1 okay. Now what should you subtract from n to make that n1 plus 1? You should subtract n2 minus 1. Why? If you subtract n2 minus 1 from n, because n is n2 plus what? n1. n1 plus n2 is n. No, so n minus n2 is n1, and minus and minus becomes plus. So that same thing you have to subtract from m1 also. Minus n2, after subtraction this becomes minus n2 plus 1, and here you have n1 plus 1. So that is also equal to 0. Okay. Now, besides these things, we now see how they are coming, but still there is something else. What was the corresponding last part of the previous calculations, which involved all the entries were the second index? The column index went up to n1. What was that thing? I mean, when we calculated a m1 n1, there also we got a chain of equalities, right? In order to turn n1 into 1, we had to subtract n1 minus 1. So from this also, we subtract this, and this is how we got 0 there. However, is every what I am trying to say here is that if you have 1 here as the second index, which you see here, does that automatically mean that it should be 0? No, there is one small point which is very easy to miss. Note that the row index starts from 2, not 1. From the fact that this first column is entirely 0, we do not get that a11 is equal to 0, because a11 is not present here. Are we getting that thing here? Yes, of course, because we have assumed m1 to be greater than n1, right? So if m1 is greater than n1, obviously m1 minus n1 is at least 1. It's an integer after all. So what I am saying here is that this difference, only m1 minus n1, is not 0. And that is why this first index is not 1. It is greater than 1. And that is why this is equal to 0. So this is where that supposition that m1 is greater than n1 has been used. And the similar supposition we also have here automatically, because n1 is greater than or equal to n2. So since m1 is greater than n1 according to our supposition, so it's also strictly greater than n2. Okay, so that's why here also we have 0. So what does that tell us? All these things tell us. It tells us that this row means not in this matrix, think of it in the original matrix A, where it is really the row m1, consists of all 0 entries. In fact, let's write that. Thus, or we can write this itself, am11, am12, and so on, am1n are all equal to 0. But if a matrix has a row which is entirely 0, can it be invertible? No, of course not. But then A is not invertible, which is a contradiction. Thus, our supposition is wrong. i.e. So what was our supposition? That m1 is greater than n1, which is wrong. That means m1 should be less than or equal to n1. Similarly, one can prove that m1 simultaneously is also greater than or equal to n1. Thus, they are equal. But then what is m2? m2 is n minus m1. So now it becomes n minus n1. However, n minus n1 is n2. So that's how m2 and n2 are also equal. And that's it. So that's what we had to prove. If they are similar, then the matrices have to be identical. They have to be the same matrix, exact same matrix. So this is where the solution ends. The next exercise is also similar, but it has 3 diagonal blocks. And there is a star also, so it's going to be somewhat difficult. I am not exactly sure whether this difficulty will be computational or conceptual. We will see, okay. I haven't solved it yet. So we will solve that in the next linear algebra video. And tomorrow, as usual, we have analysis. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.